All right, so this is going to be a quick video on how to write structural formulas or Lewis structures for covalent polyatomic ions. Okay, so remember, polyatomic ions are the ions that are in the back of your periodic table. We do it essentially the same way. There's one little twist when we are writing formulas, structural formulas for ionics, for polyatomic ions, and that is where when we are counting up the numbers of valence electrons that each atom brings. So I've got two examples here. We'll start with hydroxide. It's a pretty simple polyatomic. It only has two atoms on it, two atoms that are a part of it. So I start with, and we'll do this one later. So we start the way we start with all of our Lewis structures. We start by counting up the total number of valence electrons that we have to work with. Remember, it's the valence electrons that form the bonds in compounds. So we have to know how many valence electrons we have that we can work with to put in bonds and lone pairs. So I've got one oxygen and one hydrogen here. I know an oxygen brings 6 valence electrons with it, and a hydrogen brings 1. So in this structure, with one oxygen and one hydrogen, there are a total of 7 valence electrons. I want you to take notice of something. And the notice I want you to take is of the fact that we've got an odd number of valence electrons here. There are 7. However, if we look at the formula for hydroxide, we know that there's a charge on it. It's got a negative charge. That means that there is one extra electron than proton in the overall structure of hydroxide. Okay, so if oxygen has 6 protons and hydrogen has 1 proton, I have 7 protons altogether, and overall it has a -1 charge, which means I've got 1 more valence electron that I need to add to it. And watch what happens. I've got 8 valence electrons, which will make this a little bit more straightforward. So if when you are adding up numbers of valence electrons and you notice that you've got an odd number, chances are you've got an ion and you haven't yet accounted for the charge. If you have a negative charge, that means you've got to add electrons to the total. If you've got a positive charge, like we have up here, you are going to subtract electrons from the total. Okay, because if you have a positive charge, you have fewer electrons than protons, so electrons have gone. All right, I only have 2 atoms here, so I'm just going to throw a bond in between them. There it is. Right now, hydrogen is super happy because it's filled with 2 electrons. That bond, just to remind you, that dash represents a bond, in this case a single bond, which represents 2 valence electrons. So when you see these lines, they represent 2 electrons. Now, I've gotten rid of 2, I've placed 2 in a bond, which means I have 6 left over. I think you're going to be able to figure out where they go. They go on the oxygen to give oxygen an octet. Okay, so now the hydrogen has 2, the oxygen has 8. Both of them can have accommodated all the electrons that they can accommodate, no more, no less. Because it is an ion, I indicate that with a square bracket and the negative sign outside of it. These brackets and this negative sign are just as much part of the structural formula, in my humble opinion, as what's inside of it. So don't forget to bracket your ions and put the charge on the outside. Now you might say to yourself, well, wait a second, Ms. Vargas, don't you remember when we were looking at the periodic table and you said there's a pattern there and that carbon likes to have 4 bonds and nitrogen likes to have 3 bonds? and oxygen likes to have 2 bonds with 2 lone pairs. That's not happening here, and I would say to you that is correct. When you have ions, that pattern of 4 bonds for carbon, a lone pair and 3 bonds for nitrogen, 2 bonds for oxygen, and 2 lone pairs, that pattern might not hold anymore. Sometimes it does, often it doesn't. Okay, so yes, this oxygen does not have 2 bonds and 2 lone pairs. It has 1 bond and 3 lone pairs. It's an ion though, so that is more likely to happen than if you had an uncharged, if you had a neutral particle. Okay, so this pattern holds much better for neutral atoms than it does for ions. Okay, so if you are going singly by this, you need to rethink that when you see a positive or negative sign. Okay, let me erase this. Let me erase what I've written, and I'll clean up, and we'll do an example of something of an ion that has a positive charge, or a polyatomic cation. Okay. NF4 plus. I start by being an electron accountant. I figure out how many I have to work with. I've got nitrogen. Nitrogen brings 5. I've got 4 fluorines. Each fluorine has 7. That's 28. When I add those up, that gives 33, and I have an odd number of valence electrons again. I look to double check, and yes, indeed, I have a charge, which means I need to either add or subtract electrons from the total I have here. Because this is a positive charge, that means I have one more proton than electrons, so I'm going to subtract an electron. Right? So when I have a positive charge, I take away the number of electrons. If I had a +2 charge, I'd take away 2 electrons. If I had a +3 charge, I would take away 3 electrons. But my charge is +1, so I'm going to take away 1 electron, which gives me 32. Nitrogen will be the central atom, just based on where it is on the periodic table. It's closer to the center, and nitrogen is going to be bonded to the 4 fluorines. When I have those 4 bonds on nitrogen, that places 8 of those electrons in bonds, and now I have 24 left that I can place in lone pairs around the nitrogen atoms, and each of them will take 6. 6 times 4 is 24. So I've placed those 24, and I am good. I've placed all 24 valence electrons that I have. Now, again, because this is an ion, I put it in brackets. And I add the charge to the outside. Okay. So when you are doing Lewis structures for ions, polyatomic ions, don't forget the brackets. That is an important part of the structure as well, and the charge. All right, so that is how you do ions. The only difference is that you're either subtracting electrons or you're adding electrons based on whether your charge is positive or negative. Oh, before I go, let me just bring this up again, right? Nitrogen likes to have 3 with a lone pair, and again, because this is an ion, this guideline doesn't work in this case. Fluorine is still good, right? It agrees with that pattern on the periodic table with one bond and 3 lone pairs, but in this case, the nitrogen has to have 4 single bonds and no lone pairs. I'm going to get rid of that. All right. So, under 10 minutes. Yay me. That's kind of unusual. Hopefully that will be helpful for you if you need help as you're doing the rest of the blue packet today or tomorrow or this weekend, whenever you do it. All right. See you on the flip.